So we'll be breaking down biochemistry into 3 sections. The first starts with the basics of chemistry. In discussing the basics of chemistry, our vocabulary is going to focus around parts of the atom, so protons, neutrons, electrons, what happens when those atoms get excited, ground states and excited states, how atoms of the same element can differ, isotopes, radioactive and radioisotopes and half-lives, and finally how chemicals respond to each other, ionic bonding and covalent bonding. And when it all comes down to it, what we're really thinking about is how do different chemical reactions happen? How do chemicals bond? Because the way that atoms bond and their chemical properties are going to determine what else happens with them biochemically. And at the end of the day, all cells are just compartments to separate all the different reactions that happen in your body. So really, cells are just sacs so that reactions can happen on their own. So in talking about the structure of an atom, we're not even going to go in as much detail as what you do in chemistry. The important thing here is that we have a nucleus, we have protons and neutrons. Protons are positive, neutrons are neutral. Surrounding that, you have an electron cloud, which has several different energy states. And the important thing here is that the electrons are going to start to fill up in the electron cloud at their lowest energy state, or their ground state. And when you get more electrons, they begin to fill in at a higher energy state. But you can also have the ones from the lower energy state bounce up to a higher energy state, and this is the excited state. And why do you need to know this? Well, we can think of things like in photosynthesis, where we've got light coming in and getting molecules all excited, and that causes the electrons to bump up to different energy states. Just something AP kind of focuses on, whereas IB spends a little bit more time talking about the actual structure and not so much in discussing why you need to know kind of what's going on in terms of the movement there. And each element is going to be defined by what is in the nuclei, specifically looking at the protons that are in the nuclei. So if we have an element or an atom here with 6 protons in the nucleus, and we've got another one with 6 protons in the nucleus, then these are both carbon. However, you can have different amounts of electrons and neutrons and still have it be carbon, okay? However, let's say that you've got 6 neutrons here and 8 neutrons here. The mass of those atoms differs, and that means that they're isotopes of each other. So isotopes happen when you have the same number of protons, but you have different numbers of neutrons. And that changes the mass, because protons and neutrons each have an atomic mass unit of 1, meaning that here we've got something called carbon-12, because when you add up the protons and neutrons you get 12, and here you would have carbon-14, and therefore carbon-14 is an isotope of carbon-12. On average, carbon weighs about 12 grams per mole, but every now and then you get a couple that are 13 or 14, and that bumps it up. So when you're looking at the periodic table and you see something like 12.02, that means a small percentage are those slightly heavier isotopes. And every so often with the isotopes you get something called a radioactive isotope, in which they're not stable. The number of neutrons means that they're not going to last a very long time, don't have a very long shelf life. So when we talk about radioactivity, we're looking at isotopes that have, as I said, don't last as long, and so they have a half-life where you start with a certain atom, and that breaks down into smaller atoms over time. And the amount of time that it takes for half of a sample to break down from its larger component radioactive isotope or radioisotope into its stable forms. Is called your half-life. And we can use this in medicine in terms of different weights of isotopes so that you can test or see where different dyes are going in your body. And half-lives are also used in radiocarbon dating, where you can tell the age of different fossils or different rocks that are in the earth based on how long it takes for different chemicals within the rocks or within the fossils to start to break down. And probably the most important piece of information from this section is talking about bonding, and odds are you probably learned that you can have a covalent bond, which is when you have the sharing of electrons, or an ionic bond, which is when electrons are completely given up. But the truth of the matter is that there's actually kind of a continuum here, where covalent bonds happen when you have the perfect sharing of electrons. And carbon to carbon is a really good example of that. And an ionic bond is when you have a complete giving up of electrons. So say, for example, if you're taking some salt, the chlorine has taken one of the electrons from sodium and they've created an ionic bond. However, you can also have polar covalent bonds in different levels of polarity where the electrons are not shared completely equally between the two different atoms. So maybe a perfect example here would be oxygen and hydrogen, where we'd like to imagine that they're being shared really equally, but in reality it looks something more like this. And hydrogen's kind of all by itself, giving the oxygen a slight negative and the hydrogen a slight positive. So it has characteristics similar to ionic and characteristics similar to covalent bonding. We'll talk about this in the next unit in talking about water, because that polar covalent bond is going to be what makes water so important. And we really want to look into all the different characteristics of life that depend on water. So with that in mind, there's bonding, there's our first unit, and I hope you're finding it helpful.